completed solving problems on the first topic, that is analysis of stresses. Then we discussed the theory part on pressure line or thrust line, and we have also solved one particular problem. First problem we have solved. Correct? Now we will solve the next problem. Please note down. Please write the problem. So please don't simply listen to the class. Your active participation is very important. Okay. Please note the problem and solve parallelly along with me, so that it will be a better understanding for you all. Okay. Just go through the problem. A pre-stressed concrete beam with a rectangular section 120 wide and 300 mm deep supports a UDL of 4 kN per meter, which includes the sulfate of the beam. The effective span of the beam is 6 meter. Beam is concentrically prestressed by a cable carrying a force of 180 kN. Locate the position of the pressure line in the beam. Okay. It is similar to the previous problem only. Okay. We have to follow the same procedure, whatever we have followed for the previous problem. Let me write the diagram for the same solution. A rectangular beam having the length of 6 meter, correct? The cross section of the beam is 120 by 300. Sorry, it is not 120, make it 100. Okay, make it 100 mm. 100 by 250. Sorry, it is 120 only. 120 only. Let me change. 20. Okay, 120 by 250 is the cross section, and length of the beam given is 6 meter. And it carries some UDL. What is the intensity of UDL? It is 4 kilonewton per meter, correct? It is given as 4 kilonewton per meter. Length of the beam is 6 meter. Length of the beam is 6 meter. So here it is 300. Yes. I'll change it. 300. Okay. So this is what given in the problem. And he says that the effective span is 6 meter. The beam is concentrically pre-stressed by a cable carrying 180 kilonewton. Concentrically pre-stressed means the line of action of pre-stressing force is passing through the centroid of the section. That is the meaning. Okay, that is the meaning of the concentric pre-stressing force. Okay, let me write the cable along the centroid of the beam. So that concentric pre-stressing force having the magnitude of 180 kilonewton. 180 kilonewton. Okay. What is the question? Question is to locate the position of the pressure line in the beam. That is the question. Okay. So here also we have to follow the same procedure. Okay. Whatever the procedure we have followed for the previous problem, now we have to find moment at support, quarter span and mid span. Okay. Knowing the moment, you can locate the position of the pressure line or the thrust line by using this E is equal to M by P. Okay. And this E is equal to M by P formula is applicable only for straight cables. Remember. Okay. If it is the cable having some other profile, some other different profile, then procedure is different. Anyway, I will be solving a problem on that also. Now here in this problem, he says that the prestressing force is a concentric prestressing force. Okay, the cable is passing through center of the section. Okay, center of the section. So it is a straight cable. Okay, we can use E is equal to M by P formula here also. Okay. Now, or what is the next? Next step, we have to find moment at support, quarter span and mid span. Okay. P is equal to 180 kilonewton. In terms of Newton, it is 180 into 10 power 3 Newton. This is the prestressing force intensity. Now, we will write the diagram, loading diagram, so that we can find moment at support, quarter span and the mid span. Okay. So intensity of the UDL is 4 kilonewton per meter, 4 kilonewton per meter, and he clearly says that which includes self weight of the beam. Okay. The self weight of the beam is included in this 4 kilonewton per meter only. No need to calculate self weight and add it separately. Okay, it is included only. And length of the beam is 6 meter. 6 meter. First, you find the reactions at the support. Let me take the sections at quarter span. That is, quarter span means 6 by 4 means 1.5 meter. 1.5 meter, and mid span 3 meter. 3 meter. Now you can find the support reaction. Okay. Therefore, reactions at the support is equal to reactions at the support is equal to WL by 2. WL by 2. Intensity of load is 4 into 6 divided by 2. So how much it will be? 12 kilonewton, correct? 12 kilonewton. Therefore, reaction at the support is 12 kilonewton. 12 kilonewton here, 12 kilonewton. Okay. Now you can find the moment at support, quarter span and mid span. Okay. So moment at support will be, what is the moment at support? It is 0 only. For simply supported beam, moment at support is always 0. Correct? Then moment at quarter span will be equal to, so moment at this point. Okay, moment at this point. So what is moment of this 12 kilonewton about the section XX? It is 12 into 1.5. 12 into 1.5, and this 12 kilonewton is causing clockwise moment. Sign is plus minus of moment of this portion of UDL about this point. Okay, so it is minus 4 into 1.5. Okay, 4 into 1.5, if you do it, the UDL is get converted into point load into perpendicular distance. Perpendicular distance will be equal to 1.5 divided by 2. 0.5 divided by 2. So by this you will get moment at quarter span. What is the answer? You check the answer. It is 13.5 kilonewton meter. Okay, in terms of Newton millimeter, it is 13.5 into 10 power 6 Newton millimeter. Okay, similarly, moment at midspan. Okay, moment at midspan you can calculate in two ways. First way is to by using this reaction and this by taking the moment of this UDL. Okay, you can find the moment, or else we have the direct formula for a simply supported beam carrying UDL. Moment at midspan is equal to what? W square by 8. That formula you can directly use. Okay, let me use that direct formula so that it will be easy for doing the calculation. WL square by 8. W is 4 into 6 square divided by 8. What is the answer? It will be 18 kilonewton meter. Okay, 18 kilonewton meter. In terms of Newton millimeter, it is 18 into 10 power 6 Newton millimeter. 18 into 10 power 6 Newton millimeter. Okay. Now we got moment at support, quarter span and midspan. Now we can easily locate position of the pressure line or the thrust line. Okay. We know that for straight cable, the position of pressure line E is equal to M by P. E bar, let me call it as E bar because E represents eccentricity. Okay, let me take it as E bar so that we can understand as location of the pressure line or thrust line. Okay, therefore E bar support, location of the pressure line at support is M by P. M is 0, so it becomes 0 only. Then E bar at quarter span will be equal to moment at quarter span, that is 13.5 into 10 power 6 divided by pre-stressing force. How much it is? 180 into 10 power 3. 180 into 10 power 3. If you calculate the answer, you will get 75 mm. Please cross check the answers. Now, similarly, location of pressure line or thrust line at midspan. Will be equal to moment at midspan, that is 18 into 10 power 6. 18 into 10 power 6 divided by pre-stressing force 180 into 10 power 3. Okay. The answer is 100 mm. 100 mm. Now we can write the thrust line diagram. This is the longitudinal section. So we have the concentric cable. Which carries pre-stressing force of 180 kilonewton. 180 kilonewton. Okay. Now at quarter span, what is the eccentricity? At support, what is the eccentricity? At support, eccentricity is 0. Okay. At quarter span, eccentricity is 75 mm. At quarter span, eccentricity is 75 mm. Somewhere here we have the quarter span, eccentricity is 75 mm. At midspan, we have the eccentricity of 100 mm. At midspan, eccentricity is around 100 mm. Okay. If we join this, that will be the location of the thrust line or the pressure line. Okay, same values you will get in the RHS of the means other half portion of the beam because the loading is symmetric. Loading is symmetric. So here the eccentricity is, here it is 0, here it is 75, here it is 100, and here again 75 and 0. Okay, this is what the pressure line or thrust line. Very simple problem. You can easily do it. Only the thing is you need to accurately calculate the moments. Okay. If it is a straight cable, it is a very easy calculation. Directly by using this M by P formula, you can do it. Okay. I hope you all understood this problem. If there are any doubts, you can ask. Okay. So with this, we will move on to the next problem. Problem number 3. Yes. Problem number 3. Please write the problem, all of you. Meanwhile, I'll write the diagram. Okay. Okay, I hope you all written the problem. Go through it. The rectangle concrete beam 250 mm wide, 300 mm deep. I written the cross-sectional dimensions here. 300 mm deep is prestressed by a force of 540 kilonewton at a constant eccentricity of 60 mm. Okay, that 540 kilonewton prestressing force is applied at a constant eccentricity of 60 mm. Okay, let me write the prestressing force at a constant eccentricity of 60 mm. Okay. The magnitude of the prestressing force is 540 kilonewton. P is equal to 540 kilonewton. P is equal to 540 kilonewton. Okay. It is having constant eccentricity of E is equal to 60 mm. Okay. The beam supports a concentrated load of 68 kilonewton at the center of the span. Okay. Beam supports a concentrated force of 68 kilonewton at center of the span. Okay, of 3 meter. Okay, total length of the beam is 6 meter. Okay, he says that center of the span is 3 meter, then total length will be 6 meter only. Okay. Determine the location of the pressure line at the center quarter span and support sections of the beam. Neglect the sulfate of the beam. He said that to neglect the sulfate of the V. Okay, same procedure again. The P, pre-stressing force P given is 540 kilonewton. Okay, that is 540 into 10 power 3 Newton. Let me write the loading conditions along with the support condition for the calculation of the moment. So here the type of load given is a concentric load or concentrated load at center of the span section, that is 68 kilonewton. Okay. Center of the span of 3 meter means total span is 3 meter. I'm sorry. Total span is 3 meter. Okay, change it. Center of span of 3 meter. Okay. So total span is 3 meter. In the total span of 3 meter, at the center, the load is acting. Means at 1.5 meter distance, the load is acting. Okay, that is the meaning. So 68 kilonewton. First, we calculate the reactions at the support. The total length is 3 meter. So reactions at the support will be equal to reactions at the support will be equal to, what is the formula here? What is the formula here? It is W by 2, correct? Total load divided by 2. Okay. 68 kilonewton is applied at exactly center of the span. So you can just divide the reactions. You can just divide the total load for the calculation of the reactions. 68 divided by W by 2 or 68 divided by 2. Or else one more way is to by applying equilibrium equation, sigma Fy equal to 0, sigma m is equal to 0 and sigma Fx equal to 0, you can get the reactions. So as the loading is symmetric, directly it will be total load divided by 2 on both sides reactions. Okay, 34 kilonewton. Okay, so let me write the reactions here. 34 kilonewton and 34 kilonewton. Okay, so we have to calculate the moment at quarter span. Quarter span means 3 divided by 4, 0.75 meter, correct? 0.75 meter. And we have to find moment at mid span, that is 1.5 meter. 1.5 meter. Okay, now you can easily find the moment. You got the reactions. So moment at quarter span is equal to, initially moment at support, it will be 0 only because simply supported beam. Moment at quarter span will be equal to 34 into 0.75, and there is no loading between 0 to 0.75 meter. It is directly 34 into 0.75. It is 25.5 kilonewton meter or 25.5 into 10 power 6 Newton millimeter. Okay. Similarly, moment at midspan. Moment at midspan is equal to, either you can use the formula WL by 4 formula, or by using these reactions you can calculate 34 into 1.5 minus 68 into 0. So we are calculating moment at this point only. Point is lying in the line of action of force. Perpendicular distance becomes 0. So it is directly 34 into 1.5. Okay. So the answer is how much? 34 into 1.5. If you calculate, you will get 51 kilonewton meter. 51 kilonewton meter. In terms of Newton millimeter, it is 51 into 10 power 6 Newton millimeter. Okay. Now you can find location of the pressure line. We know that for straight cable, the location of pressure line E bar is equal to M by P. Okay. Therefore, location of pressure line at support is equal to moment at support divided by prestressing force. Moment at support is 0, so it becomes 0 only. Therefore, E bar quarter span is equal to at quarter span, moment at quarter span 25.5 into 10 power 6 divided by prestressing force P, 540 into 10 power 3. 540 into 10 power 3. The answer, if you calculate, it is 94 point. Sorry. It is 47.22 millimeter. Then location of pressure line at mid span will be equal to moment at mid span divided by prestressing force. Moment at mid span is 51 into 10 power 6. 51 into 10 power 6 divided by 540 into 10 power 3. Okay, the answer is 94.44 millimeter. Okay, now you can write the pressure line diagram. So here we have central axis. The cross sectional dimension is 300 is the depth. Okay, 300 is the depth. 300 depth. Okay, then let me write the cable profile. Cable profile is 60 mm from the central axis. Okay, now you can locate pressure line or the thrust line. Just see at support location of the center pressure line is 0. Okay, and at quarter span location of the pressure line is 47.22 millimeter. 47.22 millimeter means, so this is the center of the span, this is the quarter of the span. 47.22 means somewhere here it will come. Somewhere here. Okay, because this is 60 mm. Okay, one more important thing, students, this pressure line or the thrust line should be located with respect to this cable profile, not with respect to central axis. Okay, remember. Okay, the points should be marked with respect to this cable profile. Okay, whatever the formula we have now, E is equal to M by P. Okay, that formula is represents the location of thrust line with respect to the cable profile. Okay, not with respect to the central axis. Remember that. So with respect to the cable profile only, we have to look at the thrust line and the pressure line. Okay, so at quarter span it is 47.22. So total is 60. So below the central axis only it will come somewhere here. Okay, then at mid span 94.4 here. So if we join, what will be the nature of the pressure line? Remember students, for UDL, for beam carrying UDL, okay, the nature of cable pressure line will be parabolic. Okay, for beam carrying UDL, nature of pressure line is parabolic in nature. For beam carrying concentric force or concentrated force, the nature of pressure line is triangular. Okay, triangular. So this is what the pressure line or thrust line. Okay. So this completes the problem. Here we mentioned that value 94.44 millimeter. Here it is how much? 47.22 millimeter. Okay. So here it is 0. Here 47.220. Okay. So this completes the problem. Any doubts here? Before moving to the next problem. Okay, thank you. We'll move on to the next problem. Yes. Just go through it. Go through the problem. A rectangular concrete beam 100 mm wide and 250 mm deep, spanning over 8 meter, is prestressed by a parabolic cable. Okay, it is not the straight cable. The parabolic cable, for parabolic cable, this E is equal to M by P is not applicable. Okay, E is equal to M by P is not applicable. Okay. Here at the beginning only I have clearly written applicable for only straight cable. Correct? So in this problem, the cable profile is parabolic. We cannot use this E is equal to M by P formula. Okay. So we have to use conventional method. Conventional method means we have to first prepare the stress distribution diagram. Then we need to locate the centroid of the stress distribution diagram. Then joining the centroid of stress distribution diagram at support, quarter span, mid span, you will get the location or the profile of the thrust line or the pressure line. Okay. Prestressed by a parabolic cable with prestressing force of 250 kilonewton with zero eccentricity at supports and 40 mm at the mid span. Okay. The beam supports a live load of 1.2 kilonewton per meter. Determine the position of the pressure line or the thrust line. First, write the diagram. The cross-sectional dimensions are 100 mm wide, 250 mm deep. Okay. The total span is 8 meter. Total span is 8 meter. Write the centroidal axis. Okay. Is prestressed by a parabolic cable with prestressing force of 250 kilonewton with zero eccentricity at support, 40 mm at the mid span. We have to write the parabolic cable with zero eccentricity at the support and 40 mm at the mid span. Okay, at midspan, the parabolic cable is having eccentricity of 40 mm. At support it is 0. Okay, and pre-stressing force is given, it is 250 kilonewton. Okay, so P is equal to 250 kilonewton, nothing but 250 into 10 power 3 Newton. And he says that the beam supports a live load of 1.2 kilonewton per meter. Let me write the loading on the beam. Point 2 kilonewton per meter. Okay, this is what the given data. Okay, as I said, you cannot use E is equal to M by P formula. You have to find stress distribution at support, quarter span, and mid span. Okay, and to find the stress distribution, we need all basic parameters like moment of inertia, section modulus, we need cross-sectional area, then we need moment due to live load, moment due to dead load, all those things are required, okay, to calculate the resultant stress or stress distribution diagram at any required section. This we have practiced in the previous problems, correct? So what we will do is initially we find all these basic parameters required for the calculation, then we will proceed with the solving the problem, okay? First, we calculate the cross-sectional area. A is equal to it is 100 by 250. So you'll get 25,000 mm square cross-sectional area. Then moment of inertia you can calculate. I is equal to PD cube square 12. So 100 into 250 cube divided by 12. So we'll get the answer as 130.21 into 10 power 6 mm 4. Then you can, if you know the moment of inertia, you can find section modulus. Okay, section modulus Z is equal to I by Y, where Y is equal to D by 2 for the symmetric section, total depth divided by 2, where Y is equal to D by 2, depth is 250 divided by 2, we'll get 125 mm. Okay, therefore you can calculate section modulus now. Z is equal to 130.21 into 10 power 6 divided by 125. Okay, if you calculate, so you'll get the answer as 1.04 into 10 power 6 mm cube. So for rectangular section, you can use the direct formula for calculation of this section modulus, that is BD square by 6. If you use directly BD square by 6, you will get the same answer. Well, you can calculate in that way also. Okay. Now we calculate dead load of the beam. Dead load on the beam. Dead load of beam is equal to cross sectional area multiplied by density We'll continue. Cross-sectional area is 25,000 mm square. So here you need to substitute area in terms of meter square, correct? Meter square. So it is 25,000 into 10 power minus 6 meter square. Okay, because density is in terms of kilonewton per meter cube. Therefore, it is 25,000 into 10 power minus 6. 25,000 into 10 power minus 6 into density 24. Okay. So by this, you will get the dead load of the beam as 0.6 kilonewton per meter. Okay. Live load on the beam is given. Live load on the beam is given as how much? 1.2. 1.2 kilonewton per meter. 1.2 kilonewton per meter. So by this, you can calculate the total UDL. Total UDL. Total UDL will be equal to how much? 1.8 kilonewton per meter. 1.8 kilonewton per meter. Okay. Now we need to find location of the thrust line or pressure line at midspan, quarter span, and the support. So find the moments first. Find the moments first at respective points. Write the loading condition. Total UDL is 1.8 kilonewton per meter. Span is 8 meter and it is a simply supported beam. I'll write the diagram for the same now. Total UDL is 1.8 kilonewton per meter. Okay. Span is 8 meter. Let me take the section at quarter span, means 2 meter, and one more section at mid span. Four meter. Okay, calculate the reactions at the support. Reactions at the support will be equal to total load divided by 2. It is a symmetric loading. At the support is equal to WL by 2. Okay, W into L will give total load divided by 2. 1.8. 1.8 into 1.8 into 8 meter divided by 2. What is the answer? It is 7.2 kilonewton. 7.2 kilonewton. Okay. Let me write the reactions at the support. Here it is 7.2 kilonewton. Now you can calculate moments at corresponding points, moment at support. Support is 0. Moment at quarter span is equal to 7.2 into 2 meter. 7.2 into 2 meter minus moment of this UDL. 1.8 into 2 into 2 divided by 2. Correct? To calculate the answer, it is 10.8 kilonewton meter or 10.8 into 10 power 6 Newton millimeter. Then one moment at midspan. At midspan, Either you can use WL square by 8 formula, or by using this reaction at the support, you can calculate the moment. Okay, let me use WL square by 8 formula. 1.8 into 8 square divided by 8. Okay, answer is 14.4 kilonewton meter, or 14.4 into 10 power 6 Newton millimeter. Okay. Now we got the moments. Then what else we need is, we need a eccentricity of the cable at quarter span, support and mid span. Okay, at support, the cable is having eccentricity of 0. Okay, at mid span we have the eccentricity of 40 mm, but we don't know what is the eccentricity at the quarter span. Okay, why this eccentricity is required? To calculate the resultant stresses. Okay, to calculate the stress distribution, this eccentricity is required. Okay, so in the next step, what you do is you calculate eccentricity at the quarter span. Okay, let me write the, like using this parabolic equation of the parabola, we can find what is eccentricity at quarter span. Okay, at 2 meter distance. Let me write the cable profile here below. Total length of the beam is 8000 mm, total length of the cable. Then here at the center, we have the eccentricity as 40 mm, but we are interested to calculate eccentricity at 2 meter, means 2000 mm from support. Okay, which is nothing but x here as per the equation of the parabola. Okay, and E is nothing but y. Okay, now we know that equation of parabola, we know that the equation of parabola is equal to y is equal to, what is the formula? 4hx divided by L square into L minus x. Correct? Where x is the point where the eccentricity is required, or depth of the cable is required, y. Okay. Therefore, y is equal to, here x is equal to 2000 mm. Okay. Then L is equal to 8000 mm. You can just substitute and get the answer. And h is nothing but depth at center of the cable. Okay, for 40 mm. H is equal to 40 mm. Correct? Substitute everything. You will get y. Y is nothing but what here? Y is nothing but eccentricity at quarter span. Is equal to 4hx divided by L square. 4h40x 2000 divided by L square, 8000 square into L minus x, 8000 minus 2000. Okay, by this we will get eccentricity at the quarter span. Check the answer, it is 30 mm. 30 mm. Okay. Now what we have done is, we have calculated all the required parameters for the calculation of the stress distribution diagram. Okay, for calculation of the stress distribution diagram. Okay, So as I said, the cable given here is a parabolic cable, that E is equal to M by P formula is not applicable. We have to use this principle. What is the principle? What we have to find is, we have to find stress distribution at the support, then we have to look at the centroid of the stress distribution. Then we have to find the stress distribution diagram at the midspan. We need to look at the centroid of the stress distribution. Then we have to find stress distribution at the quarter span. We have to look at the centroid. Joining all the centroids of all the stress distribution diagram will give thrust line. This is the procedure what we have to follow for this particular problem. Okay. Now to find that stress distribution, all the required parameters we have calculated. What are the required parameters? We need moment values, we need eccentricity values, we need section modulus, correct? We need section modulus. Whatever the things required, all the things we have calculated. All the basic things we have calculated. Okay. Now, what we will do? We will find stress distribution at each and every point. Okay. Each and every point means at support, quarter span, and mid span. Okay. Initially, at support, we will find the stress distribution first. Okay. At the support, stress distribution at support. Stress distribution at support. Okay. And at support, what is the eccentricity at the support? It is 0. There is no eccentricity. Eccentricity at the support is 0. And what is moment at the support? M. It is also 0. Okay. So at support, eccentricity E equal to 0 and M is also equal to 0. Okay. Now we know the formula for finding the stresses at bottom fiber and the top fiber, correct? F superior and F inferior formula. Let me open the formula. Yes. Here we have the formula. We need to utilize this formula as F superior and F inferior. Okay. So F superior is P by A minus P by Z plus MC by Z plus MQ by Z. At F inferior is with opposite signs. Okay. Let me use those formula here. F superior. Okay. Stress at top fiber is given by P by A minus P by Z plus mg by z plus mq by z plus mq by z. Okay. And here I'll rewrite this equation, P by A minus P by Z, okay, plus mg plus mq by Z. Okay, Z is common in the denominator. Therefore, P by A minus P by Z plus I will rewrite mg plus mq as m by Z. Okay, because what we have done is we have calculated sum of dead load and the live load, and for that total load we have calculated the moments. Therefore, that moment is inclusive of moment due to dead load and live load. That is why I have taken directly m. Okay. Now moment at support is 0, correct? Moment at support is 0. M is 0, so this term becomes 0. Eccentricity is also equal to 0. This term also becomes equal to 0. Therefore, F superior is equal to directly P by A. Okay, where P is pre-stressing force. It is given as 250 kilonewton. Means 250 into 10 power 3 Newton divided by cross-sectional area. How much? Area of cross-section 25,000 mm square. 25,000 mm square. So if you calculate, the answer is 10 Newton per mm square. Okay. Similarly, we have the formula for F inferior. Okay. What is the formula? P by A plus P by Z minus mg by Z minus mq by Z. Okay. Here also, by simplification, finally you will get this kind of formula. Okay. What is the formula? It is P by A plus P by Z minus M by Z, where M is sum of mg plus mq. Eccentricity is 0. This term gets cancelled. Moment is also 0. This term is also gets cancelled. If inferior value is also P by A only, you will get the same answer, 10 Newton per mm square. 10 Newton per mm square. Okay. Now, let me write the stress distribution diagram at the support. Okay. So this is the cross section. Sorry, this is the reference line. F superior is also plus 10. F inferior is also plus 10. So this is what the stress distribution diagram at the support. Newton per mm square. Okay. So overall depth is 250. If you locate the center, where will you get the center at exactly? Exactly at the center of the depth, because it is a rectangle. It is a rectangle. So here you will get the resultant at thrust of the diagram, stress distribution. Okay, let me denote it as R. So what will be the distance? Its distance will be around 125 mm, means 250 divided by 2 from the support. Now we got location of the thrust line at support. How much it is? 125 mm from bottom fiber. Okay, 125 mm from bottom fiber. Let me write here. Okay, I will write at the last one more diagram. So this completes the location of the thrust line for support section. Similarly, we have to find the stress distribution at quarter span, and we have to find the centroid. The second one, stress distribution at quarter span. Stress distribution at quarter span. Okay. First you note what is the eccentricity at quarter span. What is the eccentricity we got at quarter span? We have calculated, no? At quarter span is here 30 mm. 30 mm. And corresponding moment at quarter span is equal to moment at quarter span. How much? It is 10.8 into 10 power 6 Newton millimeter. 10 power 6 Newton millimeter. Okay. Now, same formula, F superior and F inferior. F superior is equal to, okay, I'll directly write this formula, simplified formula. Okay, P by A minus P by Z plus M by Z. P by A minus P by Z plus M by Z. This is quarter span. And eccentricity is also at quarter span. So P by A value is already known. It is how much? 10. I wanted to substitute the values once again. 10 minus P into, sorry, P value, how much? 250 to 10 power 3. 250 into 10 power 3. Eccentricity E at quarter span is 30 mm. 30 mm divided by section modulus Z. How much it is? Section modulus Z at the beginning only we have calculated 1.04 into 10 power 6. 1.04 into 10 power 6. Okay. Plus moment at quarter span 10.8 into 10 power 6 divided by section modulus 1.04 into 10 power 6. Okay. So if you calculate, you will get result of stress at top fiber F superior 13.17 Newton per mm square. Okay. Similarly, F inferior formula and utilize this one. F inferior is equal to P by A, then plus P by Z minus M by Z. Okay, where moment is moment at quarter span. P by A is 10 only. Okay, plus P by Z, same terminology. 250 into 10 power 3 into 30 divided by 1.04 into 10 power 6 minus M by Z minus 10.8 into 10 power 6 divided by 1.04 into 10 power 6. What is the answer? F inferior, if you calculate, it is 6.83 Newton per mm square. 6.83 Newton per mm square. Okay. Now you can write the stress distribution at the quarter span. So this is the reference line. F superior at top fiber, what is the value? It is 13.17. At bottom fiber, 6.83. Okay. At top fiber, 13.17. At bottom fiber, 6.83. Joining together, you'll get the stress distribution diagram. 13.17 and 6.83. 6.83. Correct? Now, the question is to locate centroid of this diagram. Correct? From bottom fiber. Okay. Let me write the resultant of the thrust line location. Okay. We need this location of the thrust line, means distance of centroid of this figure from bottom fiber we need. Correct? For that, so you can calculate the centroid by using the first principle. Okay. Or else we have the direct formula to calculate the centroid. X is equal to, please note down, it is A plus 2B divided by A plus B into L by 3. This is the formula. Okay, where A is bottom width, B is top width. Okay, L is total height. What is total height of the beam? Total depth of the beam 250 mm. 250 mm. 250 mm. Now you can substitute everything and get the answer. A is 6.83 83 plus 2 into B, 13.17 followed by 6.83 plus 13.17 into L by 3 into L by 3, 250 by 3. By this you will get the value of X. If you calculate, it is 138.21 mm from soffit of the beam. From soffit of the beam. Okay, it is 138.21 mm from soffit. Okay. Now we have got the distance of thrust line from soffit of the beam at the quarter span. Similarly, we have to do the calculation for mid span. Third one. Third one. Third one. Stress distribution at mid span. Stress distribution at mid span. Okay, where eccentricity at mid span is how much? It is 40 and moment at mid span is 14.4 into 10 power 6 Newton millimeter. E is equal to 40 mm and M mid span is equal to 14.4 into 10 power 6 Newton millimeter. Okay, therefore F superior formula is same only. I will not write it once again. F superior is equal to P by A minus PE by Z. P by A is 10 minus PE by Z. Same terminology, but except the eccentricity value. Okay. So force P is 250 into 10 power 3. 250 into 10 power 3 into 40 divided by Z. 1.04 into 10 power 6. 1.04 into 10 power 6. Okay. Then minus plus M by Z. Plus M by Z. Moment at midspan is 14.4 into 10 power 6 divided by 1.04 into 10 power 6. Okay. If you calculate the answer, F superior, you will get it as 14.23 Newton per mm square. Similarly, F inferior will be equal to, only the sign will change, correct? Only the sign will change. That is 10 plus 250 into 10 power 3 into 40 divided by 1.04 into 10 power 6 minus 14.4 into 10 power 6 divided by 1.04 into 10 power 6. By this, you will get F inferior. F inferior, you will get as 5.77 ton per mm square. 5.77 Newton per mm square. Now write the stress distribution and find the centroid, similarly as we found out for the previous case. Okay, at top fiber 14.23, bottom fiber 5.77. It is 250. Okay. So the formula, same formula, x is equal to, same formula we have to use. X is equal to a plus 2b divided by a plus b into L by 3, where a is equal to 5.77, b is equal to 14.23. Okay. Therefore, it is 5.77 plus 2 into 14.23 divided by 5.77 plus 14.23 into L by 3, 250 by 3. So x, if you calculate, you will get it as 142.63 mm from soffit. From soffit. You can mention the value here in the figure, 142.63 mm. Okay. Now you got location of the thrust line at support 125 mm, at quarter span 138.21, at mid span 142.63. Okay, you can write one more diagram. Finally, you can show the thrust line profile. None. Now write the central axis. Central axis. Then cable profile given is 0 at support, 40 mm at the mid span. Okay. Now you look at the thrust line at support. At support, the location of the thrust line is 125 mm from soffit, from bottom. 125 mm from bottom means from bottom 125. Overall depth is 250. mm. Okay. So here only the thrust line will come. And at quarter span, just look into the value. At quarter span, it is 138.21. 138.21 means somewhere here. Sorry, quarter span comes here, no? Nearly here it will come. So 138. Okay. 138 at mid span 142.63. 142.63 somewhere here. Okay. So if you join the thrust line, this will be the thrust line. So here it is 142.63 mm from soffit of the beam. Okay. And 138.21 at quarter span. 21 millimeter from soffit of the beam at quarter span. And here it is 0. So this is what? Pressure line or the thrust line. What is the difference between the previous kind of problems and this kind of problem? Okay, the main difference here is the thrust line is located here with respect to the bottom fiber. In the previous problems where we use E is equal to m by p formula, there the location of the thrust line will be with respect to the cable profile. Okay, that is the difference. Okay, this is the cable line. This is cable, and above is the pressure line. So this completes the problem. If you have got any doubts at any point of time, you can ask. Okay, thank you. So to this problems on thrust line or the pressure line is over. Okay. So we have left with one more topic, that is the last topic of this model. We'll discuss the topic, and there are some problems associated with the topic, and we'll solve the problem, and to that this model will get over. Okay. Please write the headline as load balancing concept. Write the headline as load balancing concept. Load balancing concept. It's a very simple concept. Load balancing concept means the balancing of externally applied load by providing a suitable cable profile. Okay, referring the bending moment diagram profile of the beam. Okay, providing a suitable cable profile with respect to profile of the BMD. Okay, it's called as load balancing concept. Okay, now here what we will do is, first we will calculate the nature of the bending moment diagram. Here you can see, students, I have taken a simply supported beam which is acted upon by uniformly distributed load throughout its length. Okay, simply supported beam with UDL I have taken. For that, if you find the nature of bending moment, this is what the nature of bending moment. Okay, so while providing the cable profile, okay, so as to contract this UDL, okay, contract this UDL, that is moment due to this UDL, if we provide cable profile in such a way that similar to the profile of the BMD but in opposite direction, similar to the profile of the BMD, then it will be very effective in handling the moment due to live load. Okay, therefore providing the cable profile similar to the bending moment diagram due to the external load, okay, will contract the moment due to the load. Okay, that cable action, the pre-stressing action along the cable will contract the moment due to the external load. Okay, very simple concept. Here you can see one more example I have written. Second example, simply supported beam with point load at the center. Nature of bending moment diagram is triangular shape of BMD we get. So if you provide a triangular cable profile, then it will easily contract the external moment. Here you can see in the third example, 2-point loading is given on the beam. Okay, a 2-point loading, if you calculate the bending moment, or if you draw the bending moment diagram, it will be like a trapezium. Okay, trapezoidal shape of BMD you will get. Okay, referring to the BMD, if you provide the cable profile will also be in trapezoidal shape only. Okay, which is mentioned below the figure here. Similarly, here you can see one more beam. Okay, a continuous beam with the two simple supports in between. Okay, this is what the nature of the bending moment diagram, and this is what the nature of the cable profile provided. Okay, and this eccentricity will be equal to E is equal to M by P. Okay, moment at this particular point at center divided by pre-stressing force. We will give what should be the exact eccentricity at these points. Okay, this is what the load balancing concept. Okay, repeatedly this question. Okay, even the pressure line and load balancing concept both have asked in your previous examinations. So treat this as important for the point of your examination. They will ask you to write, they will ask you to explain about thrust line or the load balancing concept. Okay, you need to give all these examples. You need to explain the same thing here. Okay. So I'll be sharing these notes. You can refer it in detail later. Okay. So based on the same principle, we will solve the problems. Okay. Based on the same principle, we will solve the problems on load balancing concept. Okay. I hope this is clear for you all. If you have any doubts, you can ask. Okay. Okay, we'll solve the problem. Unload balancing concept now. Just go through the problem. A rectangular PSC beam 400 mm by 300 mm has a span of 9 meter. Okay, the cross section is 400 by 300. Width is 400 and depth is 300.
Sir, question.
You want question? Just a minute. Okay. Okay, write the question. Meanwhile, I'll write the diagram. I hope you written the question, correct? Finished?
Yes, sir.
Okay. Just go through the problem. A rectangular PSC beam 400 by 300 mm has a span of 9 meter. Total span of the beam is 9 meter. Okay. 400 by 300 mm dimension I mentioned in the cross section here on the left figure. If the beam supports 2 point loads 30 kilonewton each at middle thread points. Okay. So beam supports 230 kilonewton force at middle thread points. Okay. I written the 2 point loads. Okay. At middle thread portions. That is 30 kilonewton force. Okay. If the eccentricity at the middle third portion is 140 mm, okay, eccentricity at the middle third portion is 140 mm. Suggest a suitable cable profile and calculate the effective prestressing force required to balance the bending effect of the load. Okay. Now what we will do? First we will solve for this. We will solve for this. Suggest a suitable cable profile. Okay. We'll solve for this, then we'll calculate the remaining. Okay, so first question is to suggest a suitable cable profile. Okay, as per the principle of load balancing concept, okay, how should be the cable profile? It should be the opposite to the bending moment diagram of the beam. Okay, so if you want to suggest cable profile, you should know what is the bending moment diagram for the beam, correct? So what you do is you find bending moment diagram for this loading case. Okay, loading case. You find the bending moment diagram for this loading case. Okay. Now, if you find bending moment diagram for this loading case, remember students, for beam with uh, loads at middle third points having equal intensity, the moment at this point, no, moment at this point, let me take this as A, this distance as B. Sorry, yeah, let me, we'll remove the notations, no problem. Okay, so moment under the load, okay, moment at this point, moment at the loading point, okay, is M is equal to W into A, okay, where A is this 3 meter distance, okay, W is 30 kilonewton and 3 meter distance, it is 90 kilonewton meter. So the moment at support will be equal to 0. It is a simple support. So moment at support is equal to 0. So moment under the load is how much? It is 90 kilonewton meter. 90 kilonewton meter. Similarly, the same intensity here, 90 kilonewton meter, and at support again moment will be 0. This is what the bending moment diagram. Okay, just you remember this formula W into A. Okay, this you have studied in strength of materials, correct? Otherwise, you can find the bending moment diagram from first principles. You need to find the reactions at supports, then you need to find moment at each and every point. Okay, in that way also you can find the BMD. If you are not able to remember the formula, it's a very simple formula. You can remember, correct? W into A. That's it. Okay, so this is what the BMD. Now you can suggest cable profile, correct? What should be the cable profile now? The cable profile is similar to the BMD, correct? But in opposite direction. Let me write the dotted line. Like this, opposite to the BMD. Okay. So here the eccentricity is mentioned. The eccentricity at the middle third portion is 140 mm. So that eccentricity you can mention here. Okay. This is what the cable profile. Okay. Therefore, the cable profile is, you write the beam diagram. beam diagram, same cable profile, whatever I have written here, I will show here. Okay. On 40 mm. 140 mm. So this is what the cable profile should be provided to contract the moment due to external load. Okay. So here, after writing the diagram, you can write a sentence. You can write a sentence. Therefore, to balance externally applied load, provide cable profile as shown in above figure. So to this we have solved this first question. Suggest a suitable cable profile. Okay. Now we'll go next. Okay. And calculate effective pre-stressing force required to balance the bending effect of the loads. This is what the next question what we have in this problem. Okay. What is the question? Calculate the effective pre-stressing force required to balance the bending effect of the loads. Question B. Okay. Question B. Pre-stressing force required to balance externally applied load. Okay. Now what you do is we calculate moment due to pre-stressing force. Okay. And moment due to external force, external bending moment. We have already calculated. Correct? M is equal to WA. W is 30 into 3, 90 kilonewton meter. Okay. The external bending moment means bending moment due to external load. We have already calculated, that is 90 kilonewton meter. Okay. Then you calculate moment due to internal pre-stressing force. That is internal bending moment. What is moment due to pre-stressing force? P into E. PE. Okay. Force into distance. Okay. Force P into distance. Force P multiplied by eccentric PE will give moment. Okay. PE is force P. It is unknown into eccentricity is 140 into 140. Okay. 140. Here he says that to find pre-stressing force required to balance externally applied load. Okay. Balance externally applied load means moment due to external load should be equal to moment due to internal pre-stressing force. That is the condition he has given here. Okay. To balance externally applied load, it has to satisfy the condition, that is for balancing. Therefore, for balancing the external bending moment, that is bending moment due to external load should be equal to internal bending moment, that is bending moment due to internal prestressing force. Okay, then only it will be balanced. So external bending moment is 90 is equal to internal bending moment is P into 140. So by this you can work out the answer for P. Okay, the answer is uh, P is equal to 90 by 140. How much will get? 90 by
0.64.
0.642. 0.642 kilonewton. Okay, 0.642 kilonewton. So in terms of Newton, it is P is equal to here. Oh, one more very important thing. Here we should be careful about the units. See here, P into 140 mm. Okay, internal bending moment we have substituted in terms of mm, but external bending moment it is in terms of kilonewton meter. Okay, so we substitute this external bending moment in terms of Newton millimeter. So that there it went wrong. 90 into 10 power 6 Newton millimeter. So that we will get the answers P in terms of Newton only. Okay, so let me substitute here as 90 into 10 power 6. Okay, because this 140 is in terms of millimeter. Okay, so you will get the answer for force P in terms of Newton now. What is the answer now? Tell me. P is equal to 90 into 10 power 6 divided by 140. How much you'll get? X 642 point, sorry, 642857 Newton you'll get. Okay, 642.85 into 10 power 3 Newton. 642.85 into 10 power 3 Newton. Okay, so in terms of kilonewton, 642.85 kilonewton. Okay, so if we apply a pre-stressing force of 642.85 kilonewton, then the external bending moment, okay, bending moment due to external load will be balanced, okay, by this pre-stressing force. That was the meaning. Okay, now we have solved one more question, next part of the question. So just moving ahead, if the resultant tensile stress at the midspan is to be made 0 due to pre-stress, self-weight and imposed load, calculate the initial pre-stressing force in the cable for the above profile. Okay, this is the last question we have to solve. Okay, question C. Question C. To calculate pre-stressing force P, okay, for resultant tensile stress. What is S? The resultant tensile stress at midspan is to be made 0 due to pre-stress plus self-weight plus imposed load. Okay, he has given one condition. Okay, the resultant stress due to pre-stress, self-weight and the imposed load is equal to 0 at the midspan. That is what the condition he has given. Utilizing that condition, you can solve for P. Okay, for resultant resultant tensile stress is 0 at midspan. Okay, and combination is what? Dead load plus live load plus pre-stressing force. Okay, so we already know the formula for calculating resultant stress due to all these combinations. Correct? Here we have resultant. E says resultant tensile stress. Tensile stress means this formula, bottom fiber. Okay, that is P by A. This formula you have to use P by A plus PE by Z minus MC by Z minus MQ by Z. You have to use. Okay, so the condition given is resultant tensile stress is 0, means F inferior equal to 0. F inferior is equal to 0. This is what the condition he has given. Using this condition, we have to solve for unknown parameter P, pre-stressing force P. Okay, we know the formula as well for this F inferior, that is P by A plus PE by Z, then minus mg by z minus mq by z is equal to 0. Okay. Now P is the unknown parameter that we have to find. Rest of the parameters we can calculate. Okay. Where A is area of cross section. Area of cross section. A is equal to 400 by 300. 400 by 300 is equal to how much you'll get? 120,000 mm square. Then Z you can calculate. Before that you calculate moment of inertia BdQ by 12. That is 400 into 300 cube divided by 12. If you calculate, you will get 900 into 10 power 6 mm4. Please cross check the answer. If you get any different answer, let me know. We'll correct it. Okay. Z is equal to I by Y. Okay. Z is equal to I by Y. Moment of inertia is 900 into 10 power 6. Y is for rectangular section, this d by 2, total depth divided by 2. Total depth is 400, 300 by 2. Okay. Therefore, yes. Yes. 6 into 10 power 6 mm cube, we will get the answer as section model Z. Then what else is required? You require mg and mq, correct? MQ is already known. Moment due to live load, it is 90 kilonewton meter. Beginning only we have calculated. Okay. Now we calculate mg. Okay. Self weight moment. mg. Okay. Dead load is equal to dead load of beam is equal to cross sectional area into density. Cross sectional area you need to substitute in terms of meter square. Remember 120,000 into 10 power 6 minus 6 meter square. So 120,000 into 10 power minus 6. Density we know it is 24 kilonewton per meter cube density of concrete. So by this you will get dead load of the beam. We will get it as 2.88 kilonewton per meter. Check the answer please. Now you can calculate moment due to dead load. Therefore, moment due to dead load is equal to Wg L square by 8. Okay. Wg is 2.88. Length of the beam, it is given as how much? 3 plus 3 plus 3, 9 meter, 9 cube divided by 8. So 9 square by 8. If you calculate mg, you will get it as 29.16 kilonewton meter. or 29.16 into 10 power 6 Newton millimeter. Dear students, I'll be continuing this class. Okay, after this completion of this problem, I will give you 10 minutes break. Okay, and again you rejoin to the same class and we will continue the class. Okay, another 2 hours. Okay, because Thagra sir is on exam duty. Okay. Now you got mg, self-weight moment. Then what else is required? mq is known, z is known. You can substitute everything and you can solve for p. You can call this as equation number 1. Therefore, equation 1 becomes mq is 90 kilonewton meter. Already we have calculated this 90 kilonewton meter. Nothing but 90 into 10 power 6 Newton millimeter. Okay. Now equation 1 becomes equation 1 becomes P by A. P is how much? It is that only we need. P by 120,000. Then plus P by Z plus P into eccentricity is 140. It is given in the problem only. Correct? By Z. Section modulus 6 into 10 power 6. Then minus mg by z, correct? Mg by z, mg is 29.16 into 10 power 6 divided by z is 6 into 10 power 6, then minus mq by z, 90 into 10 power 6 divided by 6 into 10 power 6 is equal to 0. Okay, f inferior equal to 0. So by this you can solve for p. Okay, if you solve for p, only p is the unknown parameter in this equation. You can solve for it. If you solve, you get the answer as 627.15 into 10 power 3 Newton. Okay, therefore in terms of Newton it is 627.15 kilonewton, which means that if you apply a pre-stressing force of magnitude 627.15 kilonewton, then the resultant stresses at bottom fiber at the center of the span is equal to 0. That is the meaning. Okay, so this completes the problem. If you have any doubts at any point of calculation, you can ask. Okay, students, we will stop the class. Thank you.